uh, series is actually adding so many terms. Series is, I mean, boils down to that thing. Here he says not that we have developed a reasonable theory of limits of sequences. I mean, now you know about limits, lim sub lim inf, co-sequences, etc. But you have seen is good. Your knowledge is also good, his knowledge is also good, but you have to improve writing part because that's this mathematics is actually you see by writing. It's a click no. Now, for instance, now say you are a boy. If you don't have a girlfriend, one cannot say, oh, here is a girl. Quite often we don't like many girls, no? Most of them are actually many people misunderstand me because I talk, no? But I don't like, I didn't like roughly every girl I saw. But they thought, oh, Dr. Ramasinghe is, oh, he likes me very much. Because I never say that I don't like. So, similarly, in maths, by doing it, you see it, then you begin to enjoy this rigorous writing, logical writing, analytical writing, that Albert Einstein said this, imagination will take you everywhere, that kind of statement. So here he says, but before we develop infinite series, we must first develop the theory of finite series. This is the only time I have seen some theory for finite series because, finite numbers, if you have even 100,000 numbers, you can add provided you are given time. So I wonder why on earth you have to have series. But I thought that maybe he wants to develop infinite series somewhat parallel to what we do for finite series. So with that hope, let's go through this thing. Finite series, he says 7.1.1, let mn be integers, then let I going from m to n, not infinite, only m, be a finite sequence of real numbers, assigning a real number ai to each integer I between m and n. am is a real number, am plus 1 is a real number, and so on, an is a real number. Then we define the finite sum or finite series by that sigma symbol, sigma I equals simple m to simple n ai, by the recursive formula. This is, and we don't need the recursive formula for this one. He is seeing it. What he says is, I going m to n, a sigma ai equals 0 when n less than m. That line itself is wrong. No? Now, you are considering n numbers. N numbers, no? You are considering. Let's go to the second one. I going m to. However, what he wanted to say is that if you are, say, suppose you want to sigma ai, say I going 1 to 3, you have A1, A2 up, A1, A2 and A3. So, if by any chance, if you are considering sigma ai, I going 1 to, say, 0, then there are no terms. As a result, sum will be 0. Now he is saying I going m to ai n plus, I equals m to n plus 1 sigma ai is, first you add the first n terms, then add the a n plus 1. But he doesn't have a n plus 1 term here. So he should have used in the place of n some k, no? You understand what I am saying? If he had said I going m to k sigma ai equals 0, if k less than m, because you are beginning from n, you cannot use same n over there. And over there actually you don't have a n plus 1. So he should have said I going m to k plus 1 is I equals m to k plus ak plus 1. That's how we should have defined it. So anyway, I should say maybe these Indian people wrote this thing. Doesn't matter anyway. We get the message across now. If you are adding up terms, we can say for 3, 4, 5. If you are adding to a number less than 3, since there are no terms, sum is 0. But if you are adding to something bigger than the first term, then if you are adding I going m to, sorry, I going m to n plus 1, then it is equal to I going m to sigma ai going m to n plus an. So we should write in the place of nk. Who is this? All these people that are doing this thing. Thus, for instance, we have the identities. If you are adding from m to m minus 2, no such terms, answer is 0. I going from m to m minus 1, again answer is 0. I going from m to m, answer is just a. And I going m to m plus 1, then am plus 1, and the next one is in the same boat. He is asking why. Let's not worry why. Let's go because we know it for sure. Maybe what I see is that this book sometimes try to be rigorous at places you don't have to be. But at places where you have to be, some places have to be rigorous, not rigorous. So anyway, so because of this we sometimes express I equals m to n ai less formally as am plus 1 plus and so on plus an. Okay, then remark 7.1.2. The difference between sum and series is a subtle linguistic one. Sum is, when you are given a bunch of numbers, that is the sum. Series is it appears like a sum, but it's not a sum also. So this explanation is not that good about it, but let's talk about it when it comes to infinite series. Right now, let's read this thing and go. Strictly speaking, a series is an expression of the form. That is true. Series is an expression of this form. This is mathematically, but not semantically, equal to a real number. It doesn't have to be equal to a real number. It's just an expression. When you say sigma, say you write n going 1 to infinity. If it is convergent, it is a sum. Otherwise, it is just an expression. So, but we don't have to be, because you are students now. This kind of talk is important when you become like me, like a teacher, which is the sum of that series. For instance, 1 plus 2 plus 3 plus 4 plus 5 is a series whose sum is 15. If one were to be very picky about semantics, one would not consider 15 as a series. If they are equal, if this side is a series, that side also must be a series, no? Then it is not the case. That's why they are linguistic problem, but it's not a problem for you when you are going to. There are many difficult problems in series. Okay. Despite the two expressions having the same value, they are not the same. However, we will not be very careful about this distinction as it is purely linguistic and has no bearing on the mathematics. The expressions 1 plus 2 plus 3 plus 4 plus 5 and 15 are the same number and thus mathematically interchangeable in the sense of axiom of substitution that I did not pay much attention. Can you remember? I sort of passed it. Anyway, so I just read it. If there is nothing very serious, but you have to all what is important is when you write sigma ai, I going whatever to whatever, that is just an expression only. We will, when we come to infinite series, I will say what is important. Note that the variable I, sometimes called the index of summation, is a bound variable, sometimes called a dummy variable, but better is dummy. Because whether you write I equals m to n ai or I equals m to n aj, the same thing, is a dummy, I, j, dummy. Sometimes he calls it bound variable also. He says we list some basic properties of summation below. I mean, that is also clear. If n lies between m and p, all are integers, let ai be a real number assigned to each integer I between m and p, then we have I equals m to n ai plus I equals n plus 1 to p ai. When you are adding I equals n to p, all of them. I mean, what it says is, suppose you have say 10 or 15 numbers to add. First you add this 15, this 10 numbers, then you add this 15 5 numbers, then when you add both, sum of the 15 numbers is, so it's not a big deal. But it is a lemma. Maybe this, I did not think of how to prove it because it's not interesting to spend that much time, but you learn something by writing. That goes without saying. Let m less than or equal to n be integers, a be another integer, let ai be equal to a real number assigned to each integer between m and n. Then we have that, it's like you change the variables when you are integrating things. Quite often you do that, like that. Whether you add I equals m to n, or a j minus k, j equals m plus k to n plus k, you get the same thing. Because when you put j equals m plus k, you get am. If you put j equals n plus k, then you get m. That's a such change of variable. In integration, you do it a lot. We call it integration by substitution. No? That's the word we use in integration. Same thing. So they are a lemma. Then he says, let m less than or equal to n be integers, and let ai be real numbers assigned to each integer I between m and n. Then we have I equals m to n ai plus bi is, first you had ai's, then you have bi's. That is also intuitive. Then he says, let m less than or equal to n be integers, and let ai be a real number assigned to each integer I between m and n, and let c be another real number. Then we have I equals m to n cai is c times ai. That is also very clear. No? Triangle inequality, he says, then triangle inequality for finite series, let m less than or equal to n be integers, and let ai be a real number assigned to each I between m and n. Then we have, sigma ai, you proved it for two numbers, then for any you can prove it by induction. Absolute value of the sum less than or equal to sum of the absolute values. And comparison test for finite series, let m less than or equal to n be integers, and let ai be real numbers assigned to each integer I between m and n. Suppose ai less than or equal to bi for each I, then we have, that is also clear, no? However, proofs we exercise 7.1.1. I don't know whether to assign this as exercises. One thing, however, is when you, by writing, you learn how to write logically. That is very true. One can, no, in the future we may omit some of the parentheses in series expressions. For instance, we may write I equals m to n ai plus bi simply without parentheses. This is reasonably safe from being misinterpreted, because the alternative interpretation I equals m to n, if you put parentheses over there, before vi, then it become a meaningless statement because that bi you don't know what it is. Here you are adding a1 up to am up to an, but what is that? I mean, no, which does not make any sense. The index I in bi is meaningless outside the summation since I is only a dummy variable. One can use finite series to also define summation over finite sets. That is something little important, not that much, but again we have to know it for sure. Summation over finite series. Let x be a set. Finite set with n elements, where now he is writing n belongs to n. What is his n? I cannot remember even.
0, 1, 2, 3.
0, 1, 2, 3. I am confused quite a bit. And let f x to r be a be a function from capital X to the real numbers. That is, f assigns a real number fx to each element x. F of x is a real number, that's what it means. Because for any simple x in capital X. Then we define the finite sum because we are going to have that kind of thing. That's good to know. Sometimes we write fx, x belongs to x. So, rigorously, somebody may wonder what does it mean. However, one can say what it means is, no, let's not say what it means because he says something. Emphasize as follows. We first select any bijection G from the set. Here I belongs to n, I lies between 1 and n. To x you are finding about such a bijection exists since x is assumed to have n elements. Because if x has n elements, then that set has n elements from 1 to n. Of course there are so many bijections, not only one. Then we define sigma fx, x belongs to capital X as that way. Because when you take a bijection G, G going from 1 to up to n. This set to x. If it is a bijection, G of 1 you get. G of 1 is a member in x. G of 2 is a member in x. Similarly, G of simple n also a member in x. Therefore, you can say sigma fx, x belongs to x, is equal to, you can say sigma, because G1, G2 up here, capital X is equal to G1 up to G. Capital X is because it is a bijection of capital X as n elements. So then you can say this is I going from 1 to n, f of Gi. You can say like that because G1 in other way, otherwise I mean she has been very pedantic about this thing. He could have labeled capital X as simple x1, simple x2, simple x3 and so on. So somehow he has wanted to be, really smart, I guess. This is very important. I don't know whether we are going to do it. When you have, if the sum is, you want to count something countable, then this kind of thing can be done. But if you want to add something uncountable, then it is a question what it is. So after doing series, if we have time, let's spend say half an hour on it. It's not that important, but good to know. Here, he says, let X be the three element set ABC, where ABC are distinct objects, and let fx to R be the function, fa equals 2, fb equals 5, fc equals minus 1. In order to compute sigma fx x belongs to x, we select the bijection G, because it has three elements. Then you take the bijection G 1, 2, 3 to x. One of them is C has written here. G1 equals A, G2 equals B, G3 equals C. Then instead of writing fx x belongs to x, actually exists here now. Fx x belongs to x is actually our x is ABC. If we are not that serious, we can say this is fa plus fb plus fc. That is true. But he is, using these bijections, try to make it somewhat harder than it is. G1 equals A, G2 equals B, G3 equals C. Finally, you get fa, fb, fc, because you have three numbers. When you are adding three numbers, order is redundant. You don't know, but by the way, to this day, now, according to you, whether you have, how you add is redundant for, according to your knowledge, to this day. If you are adding, say for finite numbers, if you are adding 100 numbers, it doesn't matter how you add. First you add the first one, then last one. Can you see what I'm saying? It doesn't matter. But it matters when you have infinitely many. Rearrangement of series, I show the name here. But again he came it very fast. I don't know why. Anyway, what can we do? One could pick another bijection here. He says over there he got G1 is equal to A, G2 is equal to B, G3 is equal to C. Here he says H1 is C, H2 is B, H3 is C. Again, even when you write this way, I going 1 to 3, f of Hi, H of 1 is C, then f of C. Finally the same thing. Finally the same thing, it doesn't matter. To verify this definition, actually does give a single well-defined value to sigma fx x belongs to capital X, one has to check that different bijections G from the set 1, 2, 3 up to n to x give the same sum. So I mean, in reality you have to prove that sum does not depend on G. No?
Excuse me, sir. That one, H1 is C, H2 is B, and H3 should be A.
Oh yeah, there's a typo.
Typographical error. Yeah, it's only C, H2, B, H3 is H3 is also C. Yeah, very good. You noticed that. I didn't see it because actually I read it twice or 3 times. I did not see anything new to learn. Finite summations are well defined. What he is saying is true, because if you are defining this kind of sum using a bijection in the presence of many bijections, we need to prove that final answer does not depend on the bijection. No? That's what it is. Let capital X be a finite set with n elements. Let f x to r be a function, and let G is a bijection from 1 to n to capital X, and H is also the bijection from 1 to n to x. Then whether you have I going 1 to n f of G I or I going 1 to n f of H I, they are the same. and he is proving it also. So that's why I don't want to spend too much of time. Here he says the issue is somewhat more complicated when summing over infinite sets. If you are summing over infinite sets, then it is very serious. Very, very serious. So, anyway, we use induction on n. More precisely, we let Pn be the assertion that for any set capital X of n elements and any function fx to r and any two bijections g and h from the set 1 to up to n to x, we have f of gi equal 1 to n and sigma f of hi, both are the same. More informally he says,
You're going on.
eh?
You're going on.
More informally, Bn is the assertion that proposition 7.1.8 is true for that value of n. We want to prove that Bn is true for all natural numbers n. So he is doing here, we first check the base case P0. That is something I don't know why he is. And he defines 0 to the 0 also 1. I didn't publish that book, but I think I have written. These are indeterminates, no? X to the x. Then that kind of things, I don't know why he used it. Before the course is over, I will try to find these notes and give them to you so that you will see. Anyway, we first check the base case P0. In this case, I going 1 to 0, f of gi and I going 1 to 0, f of hi, both are equal to 0 because that's the empty set. From the very first one, that kind of thing, no, by definition of finite series. So we are done. Now suppose inductively that Pn is true. That when you have n, the capital set x has n elements, so we are assuming that no matter what bijection you choose from the set 1, 2 to n to x, and answer is the same. That's what the meaning of Pn is true. We now prove that Pn plus 1 is true. Thus let x be a set with n plus 1 elements. Let f x to r be a function. So now let g and h be bijections from the set 1, 2 all the way up to n plus 1 to capital X. F and g and h are bijections. Then we want to prove that whether you choose G or whether you choose H, that sum is the same. So he has written here rigorous proof. I mean, so many things, but to you this is clear, no, without the proof. So I recommend you to read it because I can read it now. But what he is doing is he took Gn plus 1, he took x. This is an element of x. Then he wants to isolate that and prove that Gx, then whatever the value of fx is, now since it is true for n, he wants to somehow get to the, when you have n plus 1, in order to prove that, he wants to reduce this sum to n elements. That's what he is doing here. So, I don't think I should go through this thing with you. You can read it. If you don't understand anything, you can ask me. It's nothing deep. Nothing. I read it. And can you see that's what he has done? somehow he is trying to, not there. Just to finish the proof, we have, he is defining a new function h tilde, I don't know how he reads it, h bar, something like, you want me to go through it? I don't think so. If there are so many amazing things we need to learn, if we have time. Again, this remark suppose that X is a set, that Px is a property pertaining to an element simple f of x of capital X. Let f be a function from set of all y belongs to x such that py is true to R is a function. Then we will often abbreviate this sigma set of all x such that set of all x belongs to y belongs to x and py is true. Actually that is px is true, no? I mean, I don't know why he's writing. As that one, then we will often abbreviate this one as this, no? Actually we don't abbreviate, we write this one. Or even px is true, fx. I mean, there are same thing, I don't know why. When there is no chance of confusion. For instance, fx some n belongs to n greater than or equal to 2 less than or equal to 4, or I don't understand.
It belongs to capital N bar.
No, the thing I'm worried is over there fx below the sigma sign n.
Yeah.
They are not related. Yeah, anyway, you know what this, if there is something, I will read it again before we do infinite one. If there is a point to be taken, I will tell you about it. The following properties of summation on finite series sets are fairly obvious. So far everything was obvious except the rules. But do you require a rigorous proof. Basic properties of summation over finite sets. So I mean, doing this kind of things like we say in Pandit, some people, you know, that kind of thing. If x is empty, without reading the rest, sum is 0. If x consists of a single element, x0, then fx to R is a function. We have fx, x belongs to x, is, I mean, capital X has only 0, no, I mean, it would have been better instead of writing simple x belongs to capital X, simple x belongs to singleton x0. That is far better, no? I don't know. Substitution part. If capital X is a finite set and fx to R is a function and gy to x is a bijection, then he can write, I mean, if you take any other set y to x is a bijection, so far we have been dealing with 1, 2, up to n, no? So, but this says is it doesn't matter what set you use. So, I don't know, I mean, why we should spend time in proving this. Substitution. Here he says, let n less than or equal to m be integers and let capital X be the set X, all integers between n and m inclusive. If ai is a real number assigned to each integer I belongs to x, then we write sigma ai, I going into m. You can say sigma ai, I belongs to x. That's the same thing, no? Right hand side is also a1 up to a addition, no? I think, I don't know. Because he's trying to be too pedantic about very tiny things. Let xi be disjoint finite sets, so x intersection y is empty, and f is a function from x union y to R is a function. Then we have I mean, that is also clear, no? I mean, if one wants, one can write rigorous proofs because it is what x intersection y is empty, that's the reason. Linearity part, again let x be a finite set and let f x to r and g x to r be functions, then summation sigma fx plus gx, you can separate them, no? Sigma fx belongs to x plus sigma gx belongs to x. You can write rigorous proofs. My point is that, I mean, you are not, except for learning how to write logically, mathematically you don't gain anything, no? By doing this. Except for that. Of course, proving will make you rich in proof, right in the proofs. Let x be a finite set and let fx to r be a function and let c be a real number. Then that is also, you know, no? Proof. That doesn't matter. What he says is sigma cfx, and you can pull out c, no? I mean, maybe that one is easy to prove. However, these names are important when you are learning analysis. When we say linear, he says part 1, part 2. Linear, if a function f is linear, it means f of x plus y equals fx plus fy, and f of cx is c times fx. So you will be studying something called bounded linear operators, so you get that a lot. So he has put this one as linearity part 1, linearity part 2. Monotonicity, again, if fx less than or equal to gx, sum maintains the same thing, no? Triangle inequality, again the same thing. Prove exercise 7.1.2. Let's see what he says. I looked at it, but to tell you that I did not prove anything because I thought, why on earth? What is he says? See exercise 7.1.2. Exercise. It says, prove proposition, this one, hence this is not as lengthy as it may first appear. It is largely a matter of choosing the right bijections to turn these sums over sets into finite series and then applying lemma 7.1.2. I don't know. We can prove it, it's good to prove. But what I am saying is, mathematics wise, you haven't got anything. No, we have spent almost close to 40 minutes, didn't learn anything. Then remark 7.1.2, let's see what it says. The substitution rule in proposition 7.1.11 can be thought of as making the substitution x equals gy. Okay. Hence the name. Okay. Note that the assumption that g is a bijection is essential. Can you see why? The rule will fail when g is not 1 to 1. Oh, so you are not getting everything, no? From proposition C and D. Sigma ai, I going into n, is sigma AFI, so f must be a bijection from, I mean, n plus 1 m2 the same set, so that is again nothing new. Right. Now we look at double finite sums series. Double finite series of finite series. and how they connect with Cartesian products. So, since we are going to actually, let me not say what I was going to say. Let xy be finite sets and f is a function from x cross y into R be a function. Then sigma fxy, here you are adding, here first you are adding, you fix x, you fix this x, then you add y belongs to y, then you add x belongs to x. So that is equal to f of xy, xy belongs to x cross y. When you are learning double integrals, this kind of thing will be very important. But here, I mean, not that important. I guess he is doing this thing so that you will be somewhat comfortable with when you are doing double integrals or double sums. So, maybe that's why he is writing. But even if he did not write this thing, you believe it is true, no? So not only that, you can interchange x belongs to x, you can put inside, y belongs to y, you can put outside. Same thing, no? Same thing. Anyway, so let n be the number of elements in capital X. We will use induction on n. That is, we let Pn be the assertion that lemma 7.1.3 is true for any set x with n elements and any finite set y and any function f x cross y to r. We wish to prove that Pn for all natural numbers n. You understand what he is saying, no? That is the most important thing. What you need to know is, regardless of how he has written, if you have a rectangular array of numbers, whether you add rows first, row 1, row 2, row n, then you get the row totals, and then you add first column 1, column 2, column 3, column n, then you total the column sums, answer will be the same. Answer will be the same. But the problem I gave you, when it is infinite, no, it won't be. So I don't know whether by writing, going through this, we will get some way of writing at least for infinite sums, I mean infinite double series, maybe. So what he is doing, he is going to prove this thing. What he is doing is he takes capital X as n elements and capital Y is any finite set. So he is going to prove it. We wish to prove Pn for all natural numbers. Actually, for you, if you want, you take capital X is say 1, 2, 3. Capital Y is 7, 8. Then get the cross product and write this thing. You will have the same thing on both sides. I mean, you don't have to write, you can. I mean, see it very easily. He says the base case P scenario is easy. Following proposition, whatever. He is asking why. Because it will be empty, no? Empty sum. Now suppose that Pn is true, we now show that Pn plus 1 is true. So assuming Pn is true, we are going to prove that Pn plus 1 is true. Now he is taking let x be a set with n plus 1 elements. In particular, by lemma 3.6.9, we can write capital X as, we can write capital X equals x dash union singleton x0, where x0 is an element of capital X. Because capital X has n plus 1 elements, he pulled out some x0 element and the capital X dash is x minus singleton x0. So then he says, then by proposition 7.111a we have, he is saying this sum, first you sum over y, then sum over x, but he is doing is x, he can say x dash union singleton x0, that's what he has done. Linear on the set x. By induction hypothesis, this is equal to, he says, this is equal to xy belongs to x2 dash cross y plus that one. Over there only one term from x0 only. Then by proportion this is equal to, he says xy belongs to x dash cross y and xy belongs to x0 cross y. He can write like that. Then when you look at here, this is, you get this thing. So, again you did not learn anything. He is asking why as desired. So what he wants is, I guess some writing, no here. You want me to prove them on the board? No, nothing. I don't say it. Corollary, Fubini's theorem for finite series. Fubini's theorem is a very important theorem in measure theory. Fubini's theorem is a very important one, kind of difficult to prove. It means the double integrals. When we say double integrals, it's double sums. Let xy be finite sets and f x cross y to r be a function, then he is saying for fxy, first you sum over capital Y, then over capital X. Then we proved upstairs it is equal to xy belongs to x cross y. That's what we proved, first line was proved just before. That's why this is a corollary. Then he says yx belongs to y cross x. And it's the same thing. And then you change the order. Y belongs to y, x belongs to x. For finite sums, this is always true. Whether first you add the x over y and then x over, whether first you add over x then y. I think it is better if we had done this way. It is like, say, suppose sigma aij. Say, suppose you are adding 1 to m, I going from 1 to n, j going from 1 to say m. If we had proved something like this, it would have been better for you, according to me. Aij. J going from 1 to n, I going from 1 to n. When you are adding finite double sums, order is redundant. I say sigma aij, I going 1 to infinity, j going 1 to infinity. Is say range of 57, sigma aij, j going 1 to infinity, I going 1 to infinity. Is 2020 this kind of problem again? Though I wrote this kind of thing, same thing. So for finite ones, that's what I'm saying. had he written this way, you would have understood better. If you mix with capital X or this and that, then it makes it difficult for you. We have to do this problem, not now. So we are not in the infinite series, no. Anyway, this Fubini's theorem, Fubini comes on when you have double integrals or double sum. When can you, interchange the order? If it is finite, order is redundant. If it is agreed, whether you add the first rows, then total the row sums. First you add the columns, then you total the column sums. You get the same thing. So that's what he is saying here. So he is not. Can you see here, for instance, first line is coming from the theorem. Then here over there, second one he just changed. He did not ask why, how can I do it? That is the thing I am not happy. Somehow we have to do this thing. I cannot say why, because this is so. In light of SEMA 1.13, it's sufficient to show that these two are the same, but this follows from proposition by applying bijection H, hxy equals yx. Why is this a bijection? You know that. And why does this proposition gives us what we want? Anyway, so everything is clear according to me. But unclear things are on the way. This should be contrasted with example 1.2.5, because if you go to example 1.2.5, let's go to that. That is on, you have the book. This is on page 6. Page 6 in the book. You cannot go. You have the book. Page 6. Did you go to page 6 of the book?
Yes.
Can you see? You have this rectangular array of numbers. First row is 1, 0, 0, 0. Second row is -1, +1, 0, 0. Third one is 0, -1, 0, 0. Next one 0, 0, -1, +1, left over, all of them are 0. Can you see, if you fill like this, sum of the first row is 1, second row is 0, third row is 0, all of them are 0. First row sum is 1. So, first row sum is 1, second, third, fourth, all of them have sum 0. Therefore, sum of the row sums is 1. And if you add the first column, 0. Second column 0. All the columns are 0. Sum of the column sums is 0. Sum of the row sums is 1. So that's why he said here, thus we anticipate interesting to happen when we move from finite sums to infinite sums. That line is very true. That line is very true. Yeah, okay. So I don't know whether you learn anything by going through. I did not learn, because in other chapters I write proofs, no. I did not write proofs or anything. But I see he wants to make a background to what called infinite case. Now he is coming back to, not coming back, coming to infinite series. Infinite series. There are some homework problems here, I suppose. example 7.1.5, exercise. That is a good problem. That is a good problem. Again, exercise 7.1.3, he is going to finite products. So, he always talk about addition, here is talking about products. So, I will do the problem and see whether I will assign them to you. I'm asking you, I mean, do you want to prove these results in?
No.
Because you are not learning anything. You learn, of course, how to write. Other than that, you don't learn anything. So let's forget it. But I will do 7.1.3 and see whether it's good to do it. And exercise 7.1.4, you can do it. And you have, I guess, done it in A level. I guess maybe your A level teacher did it. And exercise 7.1.5 is a good problem for us. You proved the binomial theorem in class, no? So the same proof here. Now let's go to infinite series. So that is a very, very important part of analysis, infinite series. Very good. Huh? Huh. Let's see. We now ready to sum infinite series. You see. Okay, definition. Formal infinite series. A formal infinite series is an expression of that form. That is just an expression. But that when the series is convergent, that is the actual sum, not the sum. That is the sum of the infinite series. So for now it is just n equals m to infinity, it is just an expression. Where m is an integer and n is a real number for any integer n greater than or equal to m. We sometimes write this series as am plus 1 plus am plus 2 and so on. That is the, now that does not have a meaning, no, because the reason is when if you have infinitely many terms to add, even if you add till you die, how many terms will be left over to be added? You have am plus 1, am plus 2, am plus 3. Suppose you are going to add this thing, say, not am, say, 1 over 2 to the m, 1 over 2 to the m plus 1, 1 over 2 to the m plus 2. You are going to add this thing. How many terms are there to add? Infinitely many. How many terms you can add for a day? Because you have to eat lunch, take a shower, dinner, do this homework. So how many terms you think you will be able to add per day? Beginning from 2 to the m. 1 over 2 to the m. 2 to the m plus 1, 2 to the m plus 2. How many you think per day? How many terms you can add?
50.
50, okay. For that, you can add 54 a day. So for a leap year, you can add 50 times 366. Assume you are going to live another 80 years. So even if you add terms till you die, these are the terms, this many terms you can add before your death. You begin from 1 over 2 to the m, 2 to the m plus 1. Bingo, 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 bingo. If this number is say n by any chance, so this you add up to 2 to the n. How many terms are there to be added? Infinitely many. That is the problem with. That's why we are studying infinite series. No matter how many terms you add per second or per minute or per day, till you, if you add till you die. These are this many terms. N terms you can add starting from n. Leftover terms to be added is infinite. Therefore, when we talk about infinite series, in A-level you read series, no? In A-level teachers are very bad. I shouldn't say very bad, they also don't know. No. I couldn't say the name. I didn't say the name. I didn't say. Teachers don't know actually. They should at least spend 5 minutes with the students. That when you have an infinite sum, you cannot add. That is the bottom line. You cannot do it. I mean, this. You can add only these n terms, starting from 1 over 2 to the n. Then you are going to the deathbed or graveyard and the infinitely many terms to be added. Suppose you add this many terms, then you in turn comes, you start from there and again that many terms. Even if the whole world adds, we cannot finish. So we cannot add one infinite series. We cannot add. That's why I was going to ask you whether computer can add. Computer cannot be used to explain this convergence or divergence of a series. So what happens is then if we cannot add infinitely many terms, then we have to have something like the sum. No? I mean, nobody can find the square root of 2. But using a calculator or a computer, depending on the efficiency of the calculator or the computer, you may say 2.41 this and that, some 1,000 decimal places. I mean, roughly you something close by, but that's not the square root of 2. Nobody can write number of decimal places. If you even write like the way you had the series, if you begin to write the square root of 2, every day if you write 50 decimal places, these are the number of decimal places you can write, but that's not the square root of 2. Because the meaning is, if you square that number, you will never get 2. So, as similarly here, we need something like a sum, especially for engineers and physicists. I mean, they are not doing pure maths, no. They want something like a sum of this series. Or else they will wonder how many terms should be added in order to be shaped, no? Engineering is like that. So that's why sometimes they cannot understand this pure maths business. They say, that's why in Monato University they call it Ninath, when you put the epsilon. So now what we are going to learn is, though we cannot add an infinite series, something like the infinite sum. That's what we are learning. Okay, now listen here. At present, this series is only defined formally. We have not set this sum equal to any real number. The notation is of course designed to look very suggestively like a sum. But it's not actually the finite sum because the symbol, ... ellipsis. He doesn't use the word ellipsis here. 3 dots are called ellipses. To rigorously define what the series actually sum to, we need another definition. So, can you understand, when you say sum of 5 numbers, that is actual sum. But to a series, there is no sum. You cannot add. If you cannot add, how can there be sum? So we need some definition to say this is our sum. When you say sum of an infinite series, it is something we cannot do. So there is a definition, but that's not really the sum. There. Here, and going to the book, this is the definition. Let's see what it says. Let's see. Convergence of series. Let sigma n going from m to infinity be a formal infinite series. Formal means you just say n plus 1, n plus 2, that's all. For any integer capital N greater than or equal to m, we define n partial sum Sn of this series to be Sn. N equals m to n. You have done this in A level. When you are given a series, you first find the in A level problems. Say suppose you want to add sigma 1 over n times n plus 1. You want to add this thing in going 1 to infinity. What you do was in A level, you write n going 1 to infinity. You get the partial fractions here, 1 over n minus 1 over n plus 1. Now, in A level, what you do is, then you add the n going 1 to some, say capital N, 1 over n minus 1 over n plus 1. Then you say you take the limit. Capital N tends to infinity. Then you get the limit. N tends to infinity. Here, this sum is 1 minus 1 over n plus 1, no? Right? It's a collapsing sum. So then limit is 1. So sum of this series is 1. But you need to remember, no matter how many terms you add till you go to your deathbed, that answer will never be 1. However, we say that sum is 1. So that sum, and when I say here 56, oh no, not here. Here, if I say a plus b plus c, 3 terms, no, is equal to some, say 8. Here actually it is the actual sum. This is not the sum. However, the way we define this, it is like a sum. You need to be aware. Let's see. We will come to that. Now let's see anyway. Sn, you can compute Sn, no? In A level, 1 to n. Of course, Sn is a real number. If the sequence Sn converges to a limit, capital L, as n tends to infinity, then we say that the infinite series is convergent and converges to L. And we also write L is equal to that. We write like that. That side, n equals m to infinity, an has no meaning. Because you cannot add infinitely many terms. What you do is you add capital N terms, then you get the limit as n tends to infinity. If there is a limit, we say it is series is convergent, and if the limit is capital L, we write and also write L equals. But if you had to add 3 terms, we don't say this kind of thing because you can add. Since we cannot add, so now they are, from today you have, the word sum has 2 different meanings now. To this day you had only one meaning. Actual addition of the numbers. Now here there is an infinite series, nobody can add completely. But we say sum. Now when we say sum here, it's not the actual sum you know of. You understand what I'm saying, no? And write this thing and say that L is the sum of the infinite series. If the partial sums Sn diverge, then we say that the infinite series is divergent, and we do not assign any real number value to that series. Do you understand this? This definition is very important in real analysis. If you are given a series, infinite series, you cannot add. What you do is, you take the sum of the first n terms. Then you see whether it has a limit. If it has a limit, say capital L, we say the series is convergent, and the infinite sum, n equals m to infinity, an is L, we write. If it is not convergent, that means if it is Sn is divergent, we say series is divergent. That's what we say. So now you increase your vocabulary today. Sum has now two different meanings. When I give you this thing, when I say sum, they are different. No? This is an infinite sum. No? Infinite sum is not a sum. Not a sum. Actually, it is a limit of a sum. So that's not a sum. So as a result, with infinite series, maybe there are so many amazing things. This is one of them. Whenever I used to go to Royal College match day, over there you get bright, because they invite students from, I guess, all over the country. Then from other schools they send the bright ones. So I asked them two numbers, say somebody will say 55, because his father is maybe 55. Somebody will say 100. Then I tell them, I can write a series, A1 plus A2 plus A3 is equal to, no, let me write something. A4 plus A5 plus A6 plus A7 plus A8. My A is also like 9. No? This is like 9. This sum is 55. Now, what I will do is, I tell the students I can do it. With you also I can do it. I change the order. Maybe I have the first term is A8, then maybe A100, then maybe A1, then maybe A22, then maybe A2, then maybe A9. Like that. I change the order, then the sum is 100. Same number of terms, if you add in the given order, you get 55. If you shuffle around, you get 100. So, as a result, this sum is called ordered sum. O-R-D-E-R-E-D. Ordered sum. Because a whole bunch of things to learn. That's why I told you we should not spend too much time in finite series. So, you will learn how to do it before the end of the course. Now what? So, you get the definition 7.2.2, no? That's very important. That says, what is sum of an infinite series? You need to remember, sum of an infinite series is not a sum. It is actually limit of a sum. For instance, if you add 1 over 2, 1 over 3, you add 1 over 2, 1 over 2 squared, 1 over 2 to the 3, 1 over 2 to the 4 and so on. Answer is 1. It's a geometric series. First term is 1/2. Common ratio is also, common ratio is also 1/2. Therefore, the 1 half, again like this, no? Say suppose this is a square, this side is also 1, this is 1, this is 1, this is 1. You divide into 2 halves, this side is 1 half, this side is also 1 half. Then you divide into 2 parts, this 1 half, then you get this 1 4, this is also 1. Now again you divide, this one will be 1/8, this one will be 1/1. Again you divide, this is 1/16, it's also 1/16. Then again you divide, this is 1/32, this is also 1/32. Now you divide this one again, this is 1/64, that is also 1/64. Then again you divide. Like this way you can divide infinitely many times. Sometimes eventually you may not be able to do practically, but you can divide this way. So if you add all of them, answer is 1. All of them answer is 1. That is why even when you do 1 half, if you this sum, this is a geometric series, so common first term divided by 1 minus common first common ratio is 1. From this picture you got 1. Here also you got 1 by the geometric series. So anyway, we learned something very important, sum of an infinite series, what it means, and since infinite sum is not actually a sum, unexpected, when I teach in Colombo University, I always used to say, when you do maths, expect the unexpected. But you will get many things that you don't expect to happen. Alright, so we went through the definition. Note that proposition 6.1777 shows that if a series converges, then it has a unique sum. So it is safe to talk about the sum A of a convergent series. For a convergent series, limit is unique, no? So sum of a convergent series is unique. So here he has, by the way, the one we were talking, 2 to the minus n. The first sum can be verified to be 1 minus 2 to the minus n. Then if you get the limit, you get 1. What is amazing is, however, no matter how many terms you add, it will never be 1. Never be 1. It is always strictly less than 1. But we say infinite sum is 1. Same like then he is considering 2 to the n. If you take the partial sum, you get n going 1 to n, 2 to the n plus 1 minus 2, and if you get the limit of 2 to the n plus 1 minus 2 is infinity. No? So that series, you can do that, no? S capital N going 1 to capital N 2 to the n is 2 to the n plus 1 minus 2, easy to show. So that series diverges. 2 to the minus n series converges. It converges. So, did I jump? Now we address the question of when the series converges. The following proposition shows that the series converges if and only if tail of the sequence is eventually less than epsilon for any epsilon greater than 0. Does it prove it? No. this is a very important result. Let sigma n be a formal series of real numbers. Then sigma n converges if and only if for every real number epsilon greater than 0, there is an integer capital N greater than or equal to m, such that after capital N, no matter how many terms you add, absolute value of the sum will be less than epsilon. Proof C, exercise 7.2.2. This proposition by itself is not very handy because it is not so easy to compute the partial sum n going p to a n in practice. However, it has a number of useful corollaries, for instance. So, result in proposition 7.2.5 is very important. What it says is, if a series is convergent, no matter what epsilon you are given, there is an integer capital N. No, there is integer capital N. He is beginning from simple n, that's why. There is an integer capital N greater than or equal to m. No matter how many terms you add after capital N, sum is less than epsilon. That's what it is saying. So, let's prove it because it is very important according to me. Very important. According to me. So I'm not going to write the statement because the statement is over there. Let's prove it. No? Prove. If we want to prove this thing, what? Let's say there is let n be a formal series of real numbers, then converges if and only. So suppose sigma n is going from m to infinity converges. Suppose this is convergent. Can you see why engineering faculty people like this thing? Because no matter how small epsilon you choose, there is an integer, capital N. After capital N, no matter how many times you add, the sum is less than epsilon, sum of that part. So, then they will say, okay, then the sum of the series is an plus 1
To A capital N.
That's what they say. Sum is like this because they will say, you had all the terms less than epsilon. So this is the sum. So practically this is a very important thing. Engineers live on this. But the thing is, they should be told that it is convergent by somebody else. Just now, if you are adding 1 over n, 1 over 1, 1 over 2, 1 over 3, 1 over 4, after a while, 1 over so many zeros, like this. Then here, they cannot say, eventually I am adding terribly small terms. Because of this one, can you see in this one, engineers can say, okay, I will sum is this one, a plus 1. Why? What's the reason? No matter how many terms you add after nth term, plus than epsilon. But here these terms are very small, not all the sum. as a result, they cannot say then I will take some of as this one. Can you see the difference? Here it is a theorem. If the series is convergent, when you choose say epsilon, so for say Sri Lankan engineers, let's say, they choose epsilon to be 0.001, right? Because we are not that pedantic now in this country, I guess, I don't know. So, you add after capital N, no matter how many times you add, sum is less than 0.0001. Therefore, they will say, okay, sum of the infinite series is this one. And if you take this series, now this term is very much smaller than 0.001. Okay, look at here, this is terribly small. Then sum of the series is this one. You cannot say. Actually, sum of the series is infinite. So, just because you have, at the end you have terms very, very small, you cannot say series convergence. Actually, limit an equal to 0 does not imply the series converges. Suppose this thing converges, let epsilon greater than 0 be given. So, I want to prove that there is a capital N like that. No? Let Sn is capital N, let's say. N equals M to capital N, A N. No? Since series converges, since the converge series, there exists some say capital L belongs to R, such that lim n Sn equals to L. So that's what we know. Right? And you, therefore, Sn is quotient. No? Every,
Yeah.
you know that. Therefore, Sn n going m to infinity is quotient. Since I have already chosen epsilon greater than 0, thus this is quotient. What is the meaning of a sequence xn is said to be quotient if for all epsilon greater than 0? What?
There exists n in n such,
N in n.
such that a n minus a n mod of a n minus n is less than epsilon for each n and n greater than n.
I understood what he said. Suppose somebody else is sitting over there. N. I know what he, can you see? Okay, this quotient there exists. Then there exists, let's say some capital N, let's say capital N belongs to Z plus. What we do in Z plus. Capital N, what's that?
After the proof will
Oh, there M greater than or equal to simple M, such that for each say I and J, Ij greater than or equal to capital M, SI, what plus right? I should greater than J. Or is I should greater than J? SI minus SJ. That's the actual. Then they are English. Oh, there he has capital, it doesn't matter. This is true, no? However, what is this? Thus, SI minus SJ. SI is, this is then A inside N beginning from J plus 1 to capital symbol. That's the answer. No, SI minus SJ is, SI is sum from M to N, M to I. SJ is sum from M to J, right? SJ is AM plus AJ, SI is AM plus AJ plus 1 plus up to SI. So when you subtract SI minus SJ, you get this part. This sum is less than epsilon. So that is a very, very important result. If a series converges, after a while, I don't know whether after a while is the right English term, but after some time, adding more terms, though there are many terms, does not contribute much to the sum of the series. So that is why engineers like this thing. So up again, this is very important.